After knowing all this, I think that we are actually ready to actually look at all the slides over here. So I'll just compile everything within this video. Alright, hopefully, because all the concepts you have already known, so it makes things more easier to convey. And let's start. So we have an exponential signal ek is equals to r over k. Alright, for k is larger than 0, find its z transform and determine its stability. So how do we do this? Rk is your function. Alright, you're gonna z transform this dude from k is equals to 0 to infinity. Alright, z minus 1. Alright, and therefore how do we do this? Forget again, this should be minus k. I keep saying minus 1, damn it. Anyway, the first thing I need to do is to write this thing. Factorizing out my k. Alright, so my k is being factorized out over here. So I have r times z minus 1. And we find that this is actually familiar to a, the power series. You still remember the 1 over 1 minus a stuff. So we'll just sub in a as this dude over here. What do I have is this thing over here. And I can simply rewrite this as 1 over 1 minus r over z, because z minus 1, because z minus 1 is equals to 1 over z. And then I can simply rearrange by multiplying by z over z. Everything will become y over z minus r, and this is the z transform of our rk, which is, if you remember, this is the exponential term. Alright, but we want to determine the stability. Stability is just simply your z must be larger than your r. So this means that your z, normally for safety reasons, your z must be within the 1 unit circle 1, right? So therefore your r has to be smaller than 1, and that's all. This is the stability criteria for your stuff, and this is a formula that they want. Alright, z transform rk, you get this one, stability criteria, this one, and this one. So far so good, let's go. If you still remember L3v8, the video they're talking about a lot of practice question, which is dealing with this thing over here. Alright, we actually sub in uk as equals to azk. Alright, and then we do a lot of stuff. And then actually we have a cheat code to actually solve for this problem with just a few steps. What is it? Knowing all the z transform stuff, we know that uk is simply uz. Alright, is equals to 0.5, we keep it over here. And then uk minus 1 is simply u z minus 1. Alright, and minus 0.3 u k minus 2 is simply z minus 2. That's it. In fact, I should write properly. This should be like uz, in case you may don't know what the hell am I writing. Alright, uz. Then I can simply bring everything over to the other side. So to make it a quadratic equation, goes to 0. Alright, now I just bring the uz out. I factorize. What I have is to 0. Alright, actually it should be z over here, and this is z square. Sorry, because I should have multiplied the z square over here. Alright, so because these are z minus 1 and z minus 2. Sorry, anyway, you should get a feel of it, right? So I'm just simply rearranging stuff only, right? Multiply z2 into there. So I have z2 with minus 0.5z, and you just write it out and you know what I mean, because I just want to quickly go through this. Once you got this quadratic equation over here, you can solve, and eventually you get some values. Alright, we actually solve for this, so I'm not solve for you again. Alright, so next, transfer function, your input ez, and then if you were to convolution it, will become your uz output, and that's it. If you still remember, that's what we're talking about. The transfer function, ez times ez, ht times ez, you got uz. That's it, right? This one I don't know what the hell. But anyway, we'll talk about unit pulse step exponential general sinusoid, which is the z transform of all this stuff in terms of the Laplace domain. If it's 1 over s, with a unit impulse is actually z over z minus 1, if you still remember. Right, so later on we'll talk about it. This page is to talk about the unit impulse derivation. Alright, we have to talk about it. This page is the unit impulse response derivation. Alright, we'll talk about it. And this is a trapezoidal integration by unit pulse, which is the last video we talk about it. Although it's totally and different. Alright, feel free read about it. In fact, it's the same thing that they're talking about, but they're plotting it in terms of a table, so that at least it's easier for us to see. Just now we are writing everything scribbling, right? Anyway, let's continue. Yeah, just to repeat again, this one is exactly what we are doing, but in terms of a table system. Alright, convolution is just saying that E convolute H, simply like E times H, like that only, that's all. So summation, so UK is equals to this thing, I don't know what the hell is writing. Right, the UK is simply the input, alright, multiplied by the transfer function H of z. If you still remember, they are writing in terms of this. a summation of them, right? No need to do much. Maybe later on in the future we might need to do this, but just keep it, because we really understand that u naught is equals to the e naught h naught u1. When k equals to 1, you have this particular stuff. In u2, you have all this particular stuff. And just take a look of the trend over here. You can just open it up. You see e naught is e naught over here. h1 now become h2, then h2 now become h3. Alright, and then this h1 will become h2. So as you can see, there is a trend that's going down in this manner. Just take a look. Something that you need to know, but I mean, may need to know, but we didn't discuss, but at least something that you really know that is there. Is something that we have gone through. This part is telling us that the negative values of j is the sum correspond to inputs applied before time equals. It's because if you still remember, our unit step input or exponential is always when time is equals to 0 onwards. The time is equals to infinite, negative side, they are all simply 0. So we're assuming this case, then we can use a certain stuff. And therefore, this that's the case. If let's say they will assume that if it's before the time, before 0 is already somewhere with a certain input already, and like this, then this means that it's a non-casual system. Alright, if it's something like that, then this is casual, because it's something that we keep doing on and on, which is casual. I don't know, I may be wrong, just for you to think about it. This page, if I'm not wrong, is just to convert h, k minus 1, for example, to h, capital H, k, z minus 1. If it's 2, then it's z minus 2. If it's 3, then it's z minus 3, things like that. This page is just something that we have gone through in other parts of the video. For the l4v8 or l4v6, either this video, just check it out. It's just deriving it. And this thing, this notation is over here, is simply telling that it's a z transform, alright, over a certain transfer function of e and h, which is e, z, or maybe ek and hk. Alright, so you are applying this certain transform onto this stuff, and the rest should be same, because you just simply put it over behind, and then things like that. Alright, just for you to know before you forgot. This is the Bibo stability. Alright, I don't know what the hell is this talking. If you are free, just check it out. But the important stuff is that your transfer function over here, hs, alright, must be lesser than infinity. So when you input a certain input of a this is input, right? A certain input of a impulse. So you will get some information on your transfer function. If you still remember just now in the trapezoidal video, alright, in the last video I think, yeah, and we actually done that. Alright, it's just to see whether is the transfer function itself bounded output stable or not. Alright, so for the trapezoidal is infinity, therefore it's unstable, right? So let's carry on. Read this if you're free in the bus. This stable? No, not stable. We proved already. Is this equation stable? We need to input a certain input. Alright, later on, then you can calculate yourself. I'll not calculate this. If free, then you calculate. Take note that you're gonna z transform the whole stuff, right? From zk equals to 0 to infinity, and then z minus k. And then when you sub in k equals to 0, k equals to 1, you get some values, and then you just sum them up all together. You'll get something, whether if it's infinity or 0 or whatsoever, or some constant values, I don't know. Leave you to think about it. The unit step we have proved to you. The exponential we have proved to you. Z over z minus r. Next, the general sinusoid we have somewhat proved to you, because we don't know how things transit during the k stuff and things like that, but we still prove to you that there's a cosine wave, right? But anyway, we have proved to you that particular stuff already. The special case for this general sinusoid is when your rk, because it's rk cosine theta, if theta is equals to 0, it's just simply rk, and it goes back to your exponential term, because rk is an exponential system. And then if it's 1 to the power of k, is simply the unit step function, if you still remember. It's just straightforward. Not long, this page is pretty straightforward, telling you that at this particular point is simply a sinusoidal wave, because sine theta, when theta is equals to 0, is 0, so it's over here, right here. Alright, at this particular point, alright, if cosine theta, alright, is actually starting from here, and therefore you see it's starting from here right here. Alright, and over here, as you can see, is simply some form of a cosine system also. Alright, and over here is a sine system. So as you can see, it's in terms of so-called 0, and then this is and things like that. It's just pi over pi and something like that. So along this way, this point may be where is it? This point may be pi. It's the hypothesis if you're free. Alright, this is something, at least we are talking about another perspective of this graph itself in terms of the pi and the zeros and the 2 pi and things like that, how the graph will behave. Alright, just take a look only. And this is the equation to transform the S domain to the Z domain, something like that. So we have gone through. In l4v8 graph trend, you can take a look if you're free, if you still remember. This is just to tell you that S-plane to Z-plane mapping only. So therefore, in order to map, you need an equation, and therefore this is somewhat of the equation that we use in order to plot in the S domain. When you plot your roots and your poles from the S plus 2, S plus 3, it's just plot it over here, and how you translate each of the point individually into this thing over here. Alright, it's just the plotting of the thing. If you're free, check it out. Alright. If you still remember, this little thing over here is actually your damping factor. Alright, you may have something like this going on and going on. Alright, yeah, this one over here, if you still remember. Consider a signal has two complex conjugate. Alright, sketch and discuss the time sequence with various position. Alright, how do we do this? Even over here, for different pole radius, if it's 0.9, alright, if it's 0.9, if it's 0.8, alright, these are the durations, the time duration. As you can see, the further you go into the imaginary axis, the response duration actually delay. Alright, so you're actually becoming so-called, we explicitly define what is the delay. What I mean is that the delay of the decay. Alright, at this particular point over here, as you can see, it's so-called decay very fast. Alright, and as you go by, alright, at this point over here, as you go higher up, your delay actually becomes lesser fast, and all the way up till this point over here, your delay actually increases. Alright, you become less and less able to decay. So you decay in a less, how do I say, you decay with a more time. Yeah, you decay with a more time, and this is the response duration of some sort. Alright, I may be wrong over here, but at least something fairly useful. And in the future, if you think it's wrong, you just post a comment over here. Sums up all the stuff. Goodbye.